All right. Are there any questions from the last lecture? Um, no? All right. So as I review as usual, if there are questions that come up, please stop me. So uh, as you probably figured, I'm writing the notes as we go along. So we're going to slow down a little bit, take our time with non-abelian gauge theory at one loop, because I think everyone would benefit from repeating the one loop calculation. We did this for QED. I will be going over this very fast, but you will, yeah, so you will fill in the gaps in your homework, I guess. All right, so we'll do this, and I'll quickly discuss BRC symmetry, then gauge theory at one loop, and next lecture is going to be about beta functions, right? So hopefully you recall what the goal was. All right, let's get started. So in the previous lecture, in search of 4D interacting QFTs, we turned to non-abelian gauge theories. In particular, let me just not call it angles yet. In particular, consider a gauge group G, this is a Lie group, some representation R, and some coupling G, right? So the action that we wrote down has the following form: -1/4 T of R. I think somewhere along the lecture, I might call this C of R, but hopefully you recall this is just a normalization. This is trace of TATB, right? So it's just a normalization of the generators of the Lie algebra. Trace of R, F mu nu, F mu nu. A mu, the connection, and the gauge fields are Lie algebra valued. So they are matrices. And this is the form of it. This is the form of the covariant derivative that is used to define the field strength in terms of the gauge field, right? So if you call field strength was just a commutator of the covariant derivative. All right. So let's quickly talk about the adjoint representation. So first of all, in any representation, the Lie algebra generators will satisfy this relation, and these are the structure constants. They're independent of representation, FABCs. Now, of course, in representation R, we have the normalization T of R, and multiplying, so the square of this guy, we're going to give it the name C2 of R, right? So the dimensionality of the representation, I'm going to call it D of R. Capital R here is the representation. It's a label for this representation. Now, if you remember from the last semester, we said that the adjoint representation is the case where we, I call this little t, when we use, whoa, I don't know what happened. When we use the structure constants to build these Lie algebra generators. So we saw that these structure constants will satisfy this commutation relations, right? All right, and of course, this is called the adjoint representation, and the adjoint representation C2 of G is just, like this. The structure constants will satisfy this. That's how you can read off the C2 of G. Okay, every time I write G, I mean the adjoint representation, right? So for example, in SUN, in the adjoint representation, C2 of G and T of G, as I just said, I sometimes call it C of G, is N. All right? So gauge transformations. The Lie algebra valued connection, right, field, under gauge transformation will transform this way. This is the function, this is the gauge function, again, Lie algebra valued, and it will be shifted by covariant derivative, right? That is why there are these FABCs in here, right? Because in the covariant derivative, there was the Lie algebra generator, but then we're in the adjoint representation, so FABCs is there. Similarly, F mu nu A, these are the components of the field strength, will take this form. Now, importantly, we said this last time, in non-abelian gauge theories, when the structure constants are non-zero, F mu nu A, right, is no longer gauge invariant. So field strength is not gauge invariant in non-abelian gauge theories. So the analogy with QED was that field strength was the physical thing. It was E and B's, right? Those are the physically relevant things. But here, field strength itself is not gauge invariant, but F mu nu squared is traced, right? So the Yang-Mills action is fine. Good. Now, so if I ask what are the what are the observables of Yang-Mills? What are the gauge invariant observables of Yang-Mills? What would you say?
F squared.
Well, F squared is one, but Wilson loops are. But what is the form of a Wilson loop? So now mu is Lie algebra valued, so you have to put a trace outside, right? You gotta take a trace, otherwise it's not. All right. Okay. Varying the Yang-Mills Lagrangian, you're gonna get the following equation of motion. The covariant derivative of F mu nu is, which I've expanded here for you, is minus G. G is the coupling. J mu nu A. J nu A. J nu A is the non-abelian current. Again, it's Lie algebra valued. So for instance, if these are your fermionic fields, you will take the following form. Right? Are we good? Hopefully matrix contractions are clear here. All right. That was just a very quick reminder of the terminology that I'll be using, because last time I didn't specify when I'm in the adjoint or not. So we're going to be talking about adjoint representation going forward. So last time we talked about the path integral quantization of non-abelian gauge theories. We talked about gauge fixing condition that we took to be a linear condition, right? G of A of X equals 0. For instance, one gauge condition that we looked at looked like some sort of generalization of Lorentz gauge where we upgrade the right-hand side to some arbitrary function. Of course, again, Lie algebra valued because we're talking non-abelian gauge theory. There were two steps to the path integral quantization of non-abelian gauge theories. And we did this, we call this Faddeev-Popov method or Faddeev-Popov Lagrangian at the end result. The first step was the path integral over the gauge field. We split it into two parts. One part, we wrote it as after some appropriate massaging, this became an integral over the gauge transformation. So this is the volume of the gauge group multiplied by the volume of space-time, right? All the pure gauge transformations. And here's the gauge fixed version, right? So we achieved this in the way that we saw, right? So I'm going to review it. And then in step 2, so here we gauge fixed using some G. And the G we use has this arbitrary omega of A in there. In the next step, we integrated over these omega of A's with some Gaussian weight. This is just, it's a probability measure, Gaussian probability measure over functionals, right? And then there's this C variable in there, right? It just tells you about the width of this. All right, so this is just identity that we put inside the path integral. The final result was the path integral over the gauge field. We wrote it as d of lambda. So these are, understand, it's not covariant, this is path integrals, right? D of lambda, D of A, e to the power of ISA. This is the identity that we just plugged in. There is a determinant in changing the variables. We did make a change of variables, right? This Jacobian popped up. This is that determinant. And thus this is that Dirac delta function. Do you remember where this determinant came from? to stick in the gauge condition, I wanted to put this delta function, right? But this is delta function of G. I'm path integrating over A, so I have to put del G del A. Now, G itself is like a matrix, so there's a determinant, there's a Jacobian of the transformation that appears. So this is determinant of delta G delta A, right? Good? All right. So we did this, and we then noticed that, oh, we can perform this path integral over omega, right? With this guy, you perform the path integral, you get the determinant here. This is the good old integral that you had. Now, by completing the square with this term and here, this integral will give you this term. So this is the RCC, the term that we added by hand in the case of QED to a Lagrangian to impose the RCC gauge, right? RCC gauge was this, we saw that the transverse part of the photon is the only physical part. And I can, in the perpendicular direction, in the direction of the propagation, I could arbitrarily take a coefficient C or 1 over C as the coefficient of that. And in the equations of motion, if I want to arrange for such a thing, this is the term I should add, right? This is how I argued for it classically previously. Now here it comes out of the Faddeev-Fofov method. Do you remember what the point of the RCC gauge was? Why is it nice? Exactly. So to be able to invert this, right? So the propagator is the inverse of the operator, but the differential operator had zeros, right? So the differential operator is the equation of motion. Yeah.
So one thing, earlier in case of QED, we were adding that term in the Lagrangian by 100 node. But here also I can say like
No. QED is the same thing. Well, previously we did it by hand, but this is an alternative method.
I'm saying that here also I'm inserting that identity, like integration over dw, which gives me 1.
Yeah.
To achieve that. So it's kind of achieving the same thing in a different way.
Yeah, it's a different method for the same thing. This is precisely what it is, right?
And before that, initially you told something about, when you were speaking about the generators, there was something about C2R. Can you tell what is that?
C2R?
Just here in this lecture, in the first or second step. C2G, sorry.
C2G?
Yeah.
Oh, C2G is just this thing. It's like when you multiply, it's something that depends on the representation, right? You take two of the generators of the Lie algebra, multiply it, you get identity operator multiplied by number, right? They're called the quadratic Casimirs. It's just a coefficient you calculate, right? So for SUN, it's just n. And it's yeah, it's representation dependent. So C2 of G is a quadratic Casimir of the adjoint representation.
Is it the reason why we needed the normalization of the generators for
sure?
Okay, no.
Sorry, which the T of R is that T of R is here. The two are not the same, right?
Okay.
For the case of adjoint, they're the same. SUN adjoint. They're N. They're both N. Yeah. All right. So, of course, this derivation works for any gauge theory, right? In the adjoint representation, abelian or not. In the abelian case, well, actually, sorry, this is my bad. A here. In the abelian case, this guy, this determinant, is just a constant, right? Because it's independent of the gauge field, right? It's just del mu squared, del mu, right? That's just a constant. It's an overall constant. It's divergent, blah, blah, blah. But you could, what's important is that you could take it out of the A mu path integral. So it's an overall normalization. and it drops out of the calculation of correlation function or anything physical, right? Whereas in the case of non-abelian gauge theory, this is a mu dependent, it's connection dependent, and we got to deal with it. The way we dealt with this was that because this is determinant in the numerator, it's not inverse powers, we wrote it as a path integral over anti-commuting fields that were in the adjoint representations and Lorentz scalars, right? It's just an identity. This is a Gaussian integral identity, right? We call them ghosts. And we said that the role of the ghost is to make sure this determinant is there. This determinant is the Jacobian of the transformation. It's essential for the change of variables to be properly implemented, right? So it's like, it's important for gauge invariance, or it's important for unitarity. Good? All right, Feynman rules in arc-C gauge. Actually, are there any questions so far? Because this was the review of previous part. Okay. So in the remainder of this lecture, what we're going to talk about is that I'm going to quickly write down the Feynman rules for arcs in arc-C gauge, right? To just remind ourselves of what are the vertices we're dealing with. I will briefly discuss BRST symmetry because I want you guys to have seen it. It's an import. I don't think any of you guys took. Oh no, Quinn, you did. You took the course with me on topology. So, and over there we talked about gauge fields and their connections to cohomology. And here is like I'm just gonna comment on that. This we'll see. It's just going to be very, very brief. All right, so Feynman rule, and then we're gonna do a bunch of one loop diagrams. I will probably only do the gauge boson self energy today, but we'll see how we do in time. So the final form of the path integral we're dealing with has a path integral over the ghost, the anti-ghost, and the gauge field. If I have matter fields, psi, right, I'll have to path integrate over them as well. So for example, here I've included matter fields, so let me path integrate over them as well. Right? Psi bar as well. Yeah. All right. Do you remember why? Thanks for asking. In the case of, because psi and psi bar were canonical conjugates. So in the case of scalar field, we perform, so the path integral we got on the phase space was a path integral over field and the canonical conjugate pi. But we could, in the case of the Hamiltonian was second order in pi, there was no other pi dependence, right? We performed the path integral over pi and got only a path integral over phi. In the case of scalar field, the canonical conjugate was psi bar. Terms are not second order, so we had to have both path integrals. So path integral over the fermionic fields is resembles the path phase space path integral. Right, we went over that in the previous lecture part of the course. All right, so here's the path integral. Here's the Lagrange. There is the part that is just the Yang-Mills coupled to matter, right? There is the gauge fixing term, which is responsible for arc-C gauge. And then there is the ghost term. All right? I can use the integration by parts to write the ghost term in the following form. Right? I'm just putting one of these derivatives over here. That's all I've done. I've pulled this up to the other side. The propagator for the ghost field is just delta AB I over K squared plus I epsilon. Right? There's no mass term associated with it. Massless scalar, Lorentz scalar, which is transforming the adjoint of the field. All right. Oh, I call this gluon. I should call it gauge boson. So let's write down the propagators first, the Feynman diagrams. In the arc-C gauge, the propagator, we said that, of course, because we have non-abelian, so the gauge boson is labeled by mu and A, right? A, mu, A. Those are the two labels. So this is the 2-point function of the connection, gauge field, non-abelian gauge field. And here's the propagator, and then you wouldn't be surprised to see this is C is over there. This is the arc CH. C of the arc CH, right? Yep.
Why are those particular in calling a gauge boson not a simple one?
Oh, it's just because if it's SU, well, gluon is reserved for, the term is reserved for SU3, right? So it's just like, yeah, so if you're dealing with SU2, you have called, those are the W bosons and other, they have different things. And in my head, I'm thinking QCD, that's what I wrote gluon. I'm also drawing them as if they're gluon. Anyway, all right, so this is a propagator for the gauge boson. It's proportional to delta AB, not surprisingly, right? The fermion propagator is just a good old fermion propagator. The ghost, this is the propagator, we just derived it. Now, there is a ghost vertex with the gauge boson. It comes from this term, right? It comes from the fact that this is covariant derivative. If this term was absent, if we only had the propagator of the ghost, if this term was absent, as is the case in QED because the structure constants are 0, if you introduce ghost terms, there is no vertex that connects the ghost term to anything else. So it's just a decoupled sector. You perform the path integral, it becomes an overall constant, comes out, right? Now here, there's a vertex that couples it to the gauge field. Therefore, you gotta keep it. Right, so this is essential. Of course, it's proportional to FABC. So it's 0 in QED, abelian theories. This is the vertex, vertex between the gauge boson and the charged matter, right? Not surprisingly, there's TA here. Previously in QED, this was IE gamma U, gamma mu, right? Now we have two extra vertices, right? There is a vertex for the gluon gauge boson 3-point function. It takes the following form. Now it's like a mess of indices, but what is important is that it's proportional to GFABC. Do you remember why? What is, every time you see GFABC, where is it coming from? Covariant, a single covariant derivative, right? It's how a single covariant derivative is different from a regular derivative. This is a leftover term. Now, the 4-point function comes from the term with two covariant derivatives, right? That's why it's second order, G squared and FAB squared. Well, order. And these are just the correct combination of eta is just like the metric, right? Flat space metric for the Lorentz transformations to work out nicely. Any questions? Now, just in advance, if this is the Lagrangian, if you were to introduce counter terms, what kind of counter terms would you have to introduce? What do you add to what terms are you allowed to add counter terms? So let's just go through this. Could there be a counter term for the gauge boson? Was there a counter term in the QED case? No? All right. Okay, it's good that I'm reviewing this stuff. There's a counter term for the this was the fermion, the self energy of the vacuum polarization, right? The photon self energy, and there was a counter term here. Did you remember at what order it appeared? Anyway, there was a fermion. I could have a counter term here, right? There were no ghosts over there, and I had a counter term for the vertex, right? Which is proportional to G. So I have counter terms for my propagators and the only coupling that I have. Can I have a counter term for these terms? No. The symmetry transformation, if you remember the principle of symmetry was precisely this, right? And I saw that in the ON model. If you took your action, you expanded it, it looks like an infinite number of higher derivatives, but the coefficients are fixed. The relative terms of the coefficients are fixed. It's not that you could arbitrarily change them. Here, this action comes from the expansion of 1 over G or whatever is the expansion of the Yang mills. There's only one coupling there. FABC is not a coupling, it's a structure constant. It can't change. So the only thing you can add is little delta of G, right? And two counter terms here, right? And you can, if you recall word identities, gauge invariance will even relate these guys to each other. That was the case in QED. In QED, we have 3 of them, right? We call them delta 1, delta 2, delta 3. The renormalization conditions, what was the word identity? What was the origin of the word identity? Gauge symmetry. But like, when we wrote the renormalization condition for the propagator of the gauge field, right? The photon. The thing that we could have included in there was delta of M and delta of Z, right? The wave function normalization and delta of M. But delta of Z was there, but there was no delta of M. What was forbidding it? Gauge invariance. Gauge invariance forces your gauge boson to remain massless. Same here. All right. So are the Feynman diagrams clear? So renormalization, the fact that we could push all the divergences into G and these bunch of cancel them by these counter terms is kind of interesting. Yeah, it's not given already.
This question is slightly tangential to what we're discussing.
Mm-hmm.
So, for example, suppose the situation arose that for like Yang, this model, the amount of counter terms you had just by like for example, a counter term for G and for formulas and stuff. Suppose that is not enough to basically balance out all the divergences.
Mm-hmm.
Would it be possible to add some extra counter terms which do not come from these, they're not related to these couplings or extra counter terms into the Lagrangian, and that fixes everything?
So then the question is, could that term, does that term violate the symmetry or not?
If it doesn't?
If it doesn't, then you haven't written down the most general gauge invariant Lagrangian to start with. As a matter of fact, this is actually a very interesting point. There is another gauge invariant term I can write down that I've not written down here for gauge fields. It's one other one. It's actually irrelevant. Sorry, relevant. It goes in the infrared. Do you know why? Just like naive dimension counting. It has one derivative, 2 gauge fields, 1 derivative, right? Whereas the kinetic term has 2 derivatives, 2 gauge fields. So it has a lower power of P, right? At low P, it's it's larger.
That term, CP targeting, like action term.
Yeah. We'll discuss that. Correct. Yeah. So it comes that you're preserving gauge symmetry, but there are some other symmetries that you are violating.
So are we allowed to do it?
It's a question of what symmetries you want to preserve. The principles of quantum field theory start with what are the symmetries you want to preserve? You put them in there, and then you write down all the allowed terms in derivative expansion, right? Is that good?
Yeah. And
So for example, if there's a symmetry that forbids that term, it won't be generated.
So what do you call it? So the reason why gauge symmetry is so powerful is that because the symmetry is so, like the redundancy is so strong that basically they heavily restrict the number of allowed.
Yeah, the same for global symmetry. Symmetries are powerful, right? These are ways of writing down nonlinear equations. So the theory is interacting, right? This is the magic of it, right? If the theory, the part of the struggle with lambda phi 4 is that it's silly to write lambda phi 4. Why write lambda phi 4 and not other stuff, right? And all the other stuff give you hell. But here the issue, the thing is the structure of the symmetry or redundancies of the transformation that leave the action invariant are so strong that severely limit the number of options that can happen, and that helps you have a nonlinear equation, more interacting theory, BIR. All right, so we're going to switch gears for a little bit and talk about BRC symmetry. What's the point of BRC symmetry? So I just did path integral quantization, and we're going to do Feynman diagrams and beta functions and all that. But I want to quickly do a little detour telling you about a very elegant way of constructing the Hilbert space of gauge theories using mathematics, using topology. Well, I'll not get into details of that, but so what is the deal? The deal is something called the BRC symmetry. Again, the term symmetry here is like that's like redundancy, right? First step is I start with my Lagrangian, right? So this is the good old term that I had. And if you remember, I had 1 over 2c here. Or sorry, I think this is c. I might be having c the opposite places. Anyway, and this is the term. I introduce a field BA is a scalar, Lorentz scalar, and it's just of this form. If I path integral over BA, I get back my idea of above Lagrange gauge. Right? It actually looks very similar to gauge fixing freedom up to an I. So it's just like a function, I feel that I can introduce by hand. There's no dynamics associated with it. It's a Lagrange multiplier that imposes this constraint. That's all it does. Why do I introduce this? Because it's the simplest way of writing the BRC symmetry in a like linear nice form. That's why. All right, is that clear? So what the Lagrangian is? So there's an extra path integral over B of A. It's just like a Lagrange multiplier. There's no physics associated with it. There's no dynamics. This is my gauge transformation. Correct? This is the gauge transformation. And there is a Lie algebra function worth of gauge transformations. So what I'm going to do is I'm going to perform an infinitesimal gauge transformation like here, but this function, the gauge transformation function, I'm going to put it to be proportional to the ghost field, because ghost field also it was a scalar, Lorentz scalar, and had an index A. Now I immediately notice that ghost is anti-commuting, A mu is commuting, so I can't just write it down. I have to multiply it by another anti-commuting variable. I'm going to call that epsilon, right? So what is the transformation? It's just lambda of A, put it epsilon, that's some anti-commuting variable, C of A. It's a particular choice of gauge transformation. Epsilon C of A is a commuting field, right? And if I want gauge invariance to be principal, gauge invariance to be respected, this should be respected as a quote unquote symmetry, but like it's a redundancy, right? All right, so that means that delta mu A is epsilon d mu CA, because this epsilon is just it's a anti-commuting, what's it called? Grassmannian variable. So there's no time, there's no derivative or anything. It doesn't depend on space. Whoops, I apologize for these little t's. That's when I jump around from and then, yeah. So delta of lambda is going to be IG epsilon CATA psi. This is the gauge field. This is the term that I'm going to transform C of A with. CA bar is this way, and delta B of A is this. I claim this is a symmetry of the Lagrangian. We'll go through that. Actually, it's a homework problem for you in part. But hopefully it's clear that this part of the transformation, well, actually, this whole transformation leaves the first two terms in merit. I'll go through that. But before going through the details of it, the thing that I want you guys to notice here is that if I package A mu, psi, CA, all of these are like in a column as a bunch of fields, this transformation is delta of this column thing is epsilon, some Q operator phi, right? So A, C appears here, psi appears here, CA, CBCC appears here. Actually, wait a second. Is that how I want to write it down? Yeah, actually, yeah. Now, you could check this explicitly. The second, if you take this field configuration and do a variation a second time, you're going to get 0. This is a nilpotent transformation. It scores to 0. Peskin walks you through every step of that. Now, it's clear that the first two terms are invariant under it, right? Because all that I did was a gauge transformation. The first two terms are manifestly gauge invariant, right? But we have to check that what happens to these two extra terms. There was a gauge fixing term these are the terms. So these are invariant. There are these three terms that remain. B of A had no delta. Delta B of A was 0. My transformation. So this term doesn't change. All that I need to care about is these two terms. The transformation of these two terms should cancel. And it's a homework problem for you to see that the transformation of these two terms under the rules that I wrote down here cancel. The catch is you have to use the Jacobi identity. Do you remember what the Jacobi identity was? Some relation that structure constants had to satisfy. It had to do with the fact that the Lie algebra could be integrated to build a Lie group. We went through that in detail last part 1 of the course, right? So it's a problem. It's something for you guys to check. But what is important at the end of the day is a transformation we can write down, which is a fancier version of gauge transformation. But here I'm actually using the ghost field as to set the size of the gauge transformation. All right. We're interested in gauge invariant states. So what I'm going to tell you very briefly is how to construct a Hilbert space. This is not S matrices or anything. It's just like direct Hilbert space. We're interested in gauge invariant states. Q is going to be an operator in the Hilbert space, right? That performs well, not in the Hilbert space. There's a larger Hilbert space which includes a lot of unphysical stuff when you treat gauge transformation as symmetries, but we're going to cut that down to gauge invariant sector, gauge invariant states, right? So on this large Hilbert space, this Q is the generator of this gauge symmetry. Now I can actually call it a symmetry, right? Physical states should be killed by Q. It's the condition of invariance. Now, any state that's killed by Q, because Q squared is 0, you could write it in the following, has the following decomposition. Some vector A plus Q eta. A belongs to a subspace that we call H naught. It's a subspace of states such that Q kills these states, but psi is not Q of something. If psi is Q of something, then it's killed by the virtue of the fact that Q squared is 0. And then this is the extra term. This is the term. So this eta belongs to H1, subspace of states for which Q over psi 1 is not 0. Now, if I have a vector that belongs to psi 1, H1, when I act with Q on it, I get a vector in H2. This is a subspace of states that could be written as Q of sub psi 1. So the Hilbert space, in summary, splits into 3 sectors. The sector that is not killed by Q. Then there's a sector that is killed by Q that's split into 2 parts. The part that could be written as Q of something, and the part that is killed by Q but cannot be written as Q of something, right? The point is that physical states are these guys, H0s. So if you know the terminology of closed and exact, this is precisely that terminology, right? So They have to do with non-trivial cohomology. But so the physical states belong to H0, and now I'm going to argue for you that Q of eta, which is the state in H2, is pure gauge. There's a vector that's pure gauge. How am I going to argue for that? Well, let's pick two vectors that belong to H2. What is the inner product? 0. What is the inner product of a vector in H2 and size 0? That's also 0. Right? So it's pure gauge. We're just going to call that pure gauge. So the way we construct a Hilbert space is by looking at the set of vectors that are killed by Q, but they're not Q of something else, right? And any non-trivial vector, which is Q of something, is a pure gauge transformation, right? This is, now transverse gauge bosons belong to H0. You could show that the ghosts and the components of the gauge field along K mu belong to H1 and H2. They're all gauge transformation. This is the neat thing about BRC, really demystifies a lot of this stuff. And mathematically speaking, Q squared equals 0 allows you to build a Hilbert space using cohomology. I'm not going to get more into details of this. But that's just how we quantize formally gauge theories on a lattice or not. Yeah.
So what is the role which Q is actually playing? Is it to distinguish between the physical stress and the gauge limits?
Say it again.
Like, what is the role which this Q is actually playing over here? Like, it's a bit unclear to me. Like, what is the physical significance of this Q?
It is a transformation that doesn't change the physical states,
but it changes the non-physical ones.
But creates pure gauge transformation. So it's a pure gauge transformation. Q is the generator of pure gauge transformations, right? It does not act on the physical states. Good? Is this point clear? All right, so any questions? BRC cohomology? Well, start with Peskin, but like there's plenty. Actually, if you want to read more about this, the best, well, one of the good places, I learned this stuff from Weinberg. So Weinberg has in volume 2, there is it has a pretty decent discussion of the cohomology. But I would say if you want to see the role of cohomology in constructing the Hilbert space of gauge theories, start with the lattice, start with Kitaev model or something very, very simple. Those are this, V2 gauge theory. It doesn't get easier than that. And then you see the role of cohomology. Oh, I mean, Z2 is like, in toric code, it's just homology. It's homology, but yeah, it's a long story. I taught the whole course on this. There, if you want to read more, again, I can give you more references. Yeah. By the way, what does it mean that actually the connection to topology, do you guys have a sense of what the connection to topology is? The connection to topology comes from the following statement. What are the observables of the theory? Wilson loops, right? So here is a Wilson loop, right? I'm integrating over dx mu a mu of x, right? I take e to the power I, have the path ordered and traced the representation. This is a Wilson loop. Sorry if you don't see, sorry. No. Yeah, this is a Wilson loop. Now, imagine we saw that from Stokes' theorem, the value of this is proportional to the flux that goes through this. It's actually given by the flux that goes through this. Imagine the flux, which is the flux has to do with J mu. Imagine I turned off the flux. So J mu is 0, right? It means that this integral is the same as this integral. I can deform this continuously, right? The only setup where I can have something non-trivial is that there is some topological obstruction. And current actually creates some sort of topological obstruction, right? Yeah, so you could arbitrarily deform the Wilson loops if you don't have background. And the only physically relevant observables would be associated with loops that could not be shrunk to a point, right? They're non-trivial. Actually, sorry, let me just say a few more words. I'm oversimplifying a little bit. So in the case of abelian gauge theory, homology is the way we construct a Hilbert space. So cohomology is a dual picture. It's usually used in supersymmetric quantum mechanics as fancy words for like similar structure. It's a transformation between fermions and bosons. Now, for non-abelian gauge theory, homotopy is important, as I just hinted at, right? Homotopy is the way to go because it's non-abelian, right? The fundamental group is non-abelian. Homology groups are all abelian, yeah. And it's important that the Wilson loop is like dimension 1, right? Higher homotopy groups are also trivial. Abelian, sorry, are also abelian, right? So the only non-abelian structure you're going to get is just out of homotopy in this setup. Anyway, sorry, that was a tangent. All right, any other questions? So we're going to change gears and talk about non-abelian gauge theory at one loop. What are the diagrams I'll have to calculate? I'll have to calculate the 1pi gauge boson self-energy, or I think I called this vacuum polarization before, for the case of QED. The fermion self-energy, the boson-fermion interaction vertex, right? So the gauge boson self-energy, the diagrams that contribute based on our Feynman diagrams, is a fermion loop. You've already done this path, this integral. You just have to carry a bunch of generators Lie algebra. I'll just show you the. There are a couple more. There is the loop that comes from the gauge boson running in the loop. There is this term, right? And then there's a ghost term. What is, in terms of G and F, what is this proportional to? G squared, F squared, FF. What is this term proportional to? Yeah, right. So we're good. Fermion self-energy, this is a good old diagram that we calculated. Again, a bunch of lambdas go for the ride. Now, boson-fermion interaction is a little bit fancier. We calculate this diagram in the case of QED, but now we have this diagram. This was absent in the case of QED because there's no vertex for 3. QED is non-self-interacting. Photon is non-self-interacting. Now, what are the counter terms I can have? Structure is very similar to QED. I can have a counter term for the propagator of the gauge boson. And this is the form of it. So I unfortunately here, sometimes I go to the C equals 0 gauge. Sometimes I go to C equals 1 gauge. I apologize for that. I just move things around. I'll try to, yeah. We call this delta 3 in the case of QED. Delta 2 was the counter term that for the fermion propagator we introduced. And delta 1 was the counter term for the vertex. I apologize again. This is capital T. Sorry about that. Now, 3 counter terms should get rid of all the divergences that come up. Is Mills power counting normalizable? Yes. Why? The coupling is dimensionless, right? So classically, it looks scale invariant. Right? Classically, the coupling is dimensionless, which means it's marginal, classically marginal. So now the question is it gonna, like lambda phi 4, classically it was marginal, but then the question was quantum mechanically, it became irrelevant. Here we're gonna see that quantum mechanically, this becomes relevant. That's called asymptotic freedom, right? So the gauge boson self-energy. Recall the word identities. What was word identities? It's just that this guy, this 2-point function contracted with a mu, q mu should be 0. This is just the statement that there should be no degree of freedom propagating in the direction of, there should be no degree of freedom for the gauge boson along the direction of propagation, along q mu. So said differently, this 2-point function should be proportional to this. If I have a arc C gauge, there would be some, this part of it is gauge dependent, right? This was Lorentz gauge. C equals 0, right? Gauge invariance, this word identities, we saw that in the case of, so let me just remind you how the QED calculation went. In the QED calculation, we saw naively a divergence which was second order, and there was a lambda, and there was divergence that was log. The second order divergence in lambda was dangerous because it was giving a mass to the gauge boson, and that's forbidden by gauge transfer, by gauge invariance, right? We saw that word identities took care of that. We saw that actually word identities was a proof. Non-perturbative proved that that term is 0, the coefficient of it is 0, but we checked explicitly that it was 0. I'm going to repeat the essence of that calculation here in the case of non-abelian setup, right? So here it's important that log term is the only term that we care about. But gauge invariance forbids that higher offensive divergence. So here it is. This is the term. It should be familiar. This is the extra bit. This is the part that we already had. Unfortunately, again, sorry, I apologize. I'm working C equals 0 gauge. And this is the extra part. If you just put this next to QED, you see a lot of similarities. What are the steps that I went to get to this? So I use Feynman diagrams to write down this diagram. Feynman rules to write down this diagram. What are the ingredients of it? There's an integral over here. Each vertex imposes a conservation, right? I have an integral over the fermion that runs in the loop. And because the fermion, there's a minus sign, right? It's just Legos. Now, to evaluate that integral, what are the set of tricks that we played?
First is minus trick to basically write the denominator as something to the power of whatever.
Yeah, so first we dimensional regulate. We dimensional regulated, and that what it entailed was that I perform my integrals, space-time integrals over dimension d, not changing the propagator. The propagator remained 1 over q squared stuff, but the dimensionality of space-time, I just formally took it to be d. Then I did what you exactly said. I used Feynman parameters that introduce variables of, depending on how many loops I was dealing with, x and y variables. Here I'm doing one loop, is only one x variable. Then I did 2 change of variables. The thing that was integrating on the loop is called k. I redefined a new variable L, which was k minus xq, the external thing, right? I defined this object called delta, if you recall, and I rearranged the integral. The key part was that the final form had an integral over x variable from 0 to 1. That's the x of the Feynman parameters, right? So this is what that result is. Then the last step of the calculation was that we talked about going near dimension 4, right? 4 minus epsilon, and in that expansion, we saw that the coefficient of the log term is 1 over epsilon, right? We isolated that term. We discussed the MS bar scheme, blah, blah, blah. You remember all of that. So this is where it comes from. Good. Now, if you have NF fermions, each of them contribute by the same amount, and NF is just multiplied by this, right? Let's say the fermions don't talk to each other directly. All right. So that was the first diagram that contributes to the gauge boson propagator. The other diagram is the 3-point function of this. So you will go through the pain of calculating this in your homework. This is the form of it. Again, the same 3 steps. Dim reg, Feynman parameters, define this variable and these variables. Hopefully they're familiar. The key, one extra trick that we played was that delta was x symmetric under x going to 1 minus x, right? That we use that to kill some of the terms, to argue that some of the terms vanish, right? All right, so this is the expression. You shouldn't be surprised that there are terms of this type. Where do they come from? There are two of such vertices, and there are these combinations in such vertices, right? So order G squared, as it should be. Good. All right. Now there is, oh, wait, what? Oh, yeah, so sorry. So here I just wrote the Feynman, no, here I simplified it. But what the structure I want you guys to keep track of with flashing these expressions is I want you guys to keep track of this. The coefficient of this term. What is special about this term?
Is the divergence, is what divergence of D before.
It has a pole at D equal 4. That leads to the log divergence, right? Now here I have terms that are like that. The coefficient, so here the coefficient of it is what? Q squared eta mu minus QQ nu. Here I have two terms with the first part of the coefficient, the second part is minus Q nu, but these two terms don't match. However, if you use the x going to minus 1, x going to 1 minus x symmetry, you see the coefficient of the two match. Right? I'm just giving you tricks to do your homework. Right? So the end result of each of the diagrams, what we get is a bunch of like kinematic terms that are outside. Then there's an integral over d of x. There's always this factor. Now there are the coefficient of 1 minus d over 2 terms and the coefficient of 2 minus d over 2 terms. These guys are contribute to the logs. What does this term contribute to? This is a horribly offensive term. This violates. This is the square divergent, the terms that quadratically diverges. So if you recall, if you go back to the discussion we had last time, the term that was awful was precisely this gamma 1 minus d over 2. Near d equal 2, it shows this pole. So we'll see that cancels. The coefficient of this term cancels. You do this diagram. Again, similar structure. There's the really offensive term and there's a log term. Right? You should know immediately that every time, so these two terms are okay, they're q squared, proportional to q squared. So they're in a sense transverse, right? Because the q mu, q nu part is all gauge, right? This term is all gauge in a sense, right? This term is not. This term is not. And then there is the ghost term. The ghost term has a coefficient of both of these two. All right, so what is left to do? Just add up all of these diagrams, put the three diagrams together, and we're going to look at the coefficient of the really horrible term, which is this gamma 1 minus d over 2. The coefficient of that is going to be q squared x 1 minus x, d minus 2 times 1 minus d over 2. Now, 1 minus d over 2 is precisely a term that cancels this pole. What do you get? You get gamma 2 minus d over 2. Right? This was guaranteed by ward identities. Ward identity is guaranteed that like non-perturbatively there won't be any problem. But here you're seeing it as one loop. So this is smooth. The coefficient of that awful term just drops. So the quadratic divergent term is just not there. And it's important that you see the ghosts contribute the right amount to cancel that divergence. So the role of the ghost is really gauging merits. All right. Now that we cancel the coefficient of this awful term and it became just a normal regular term, let's repackage all the terms are proportional to gamma of d minus 2 minus d over 2. They're all log divergent. So let's repackage all of them. They look like this. So there's gamma of 2 minus d over 2, eta mu nu q squared. This is the coefficient of it. In the interest of time, I'm saving you the trouble of talking about the symmetry of x going to 1 minus x. You use that symmetry to write everything in the following form. So this is the full answer at one loop for the propagator of the gauge boson. IG2 y, because it's one loop, right? Delta AB. Hopefully you remember why this should be proportional to delta AB. This form is guaranteed. This means it's transverse. Right? This is the coefficient and gamma of 2 minus d over 2, and then this guy. If you go back to the QED calculation, this part is present, well, appropriate parts of it, right? Well, this is also a QED calculation, right? Just put the abelian answer in there. All right, so you take a look at this. I'm gonna leave this for you guys to work out in detail. But if you recall, what did we do with this? Extracted the divergent term in the MS bar scheme. That coefficient is this minus 5 over 3. But it's minus 5 over 3 in C equal 1 gauge. If you repeat this calculation in a general RC gauge, it's minus 13 over 6 minus C over 2. The self-energy is gauge dependent. The self-energy of the boson vector field is gauge dependent. These are things that you have to be very careful. As you probably by now you've seen, as you go from abelian case to non-abelian case, a whole bunch of things become gauge dependent. Right? All right. So in summary, let me summarize. What did we do today? Right? I very briefly started, actually, what did I do at the beginning? Yeah, I just went over a little bit of the gauge. I reviewed the Fediev-Popov, right? We discussed the Feynman rules, right? We discussed the Feynman rules. The important part was that the ghost had a vertex with the gauge field, not the fermion, right? Only the gauge field. It was coming from the determinant of the del mu of the covariant derivative. As proportional, it's coming from the expansion of the covariant derivative, right? These Feynman, these vertices are the things that you should have in mind, right? These vertices are the things that you should have in mind. This is perhaps the most important quantum field theory we've ever constructed. It describes nature. SU3 cross SU2 cross U1 is this theory. It's just a particular shape of standard model particle because it's this. That's it, right? All right. We did that. Then we discussed the BRSC symmetry. The point of BRSC symmetry was that we cooked up at the level of the Fediev-Popov Lagrangian a symmetry that looked like a gauge transformation, but the generator of it, the generator of the gauge transformation was proportional to the gauge field. Of course, the coefficient of it had to be an anti-commuting thing. And that ensured that Q squared was 0. Then we saw that, well, because the gauge invariant states are the physical states, we were after states that were killed by Q. Now, an arbitrary state that's killed by Q could be written as a vector that is killed by Q, but it's not Q of anything, right? So it's close but not exact, right? And a term which is exact, Q of something, right? We said Q of something, that exact part is pure gauge, right? And the part that was close but not exact, the cohomology part, is the physically relevant states, right? Okay, then we discussed very briefly, I just flashed a bunch of integrals, but I think by now you should be pretty used to them. We discussed the perturbation theory for non-abelian gauge theory. There are three diagrams, three diagrams that we had to be careful with. of course, the same with QED, right? So one of the two propagators for the fermion and for the gauge boson and the vertex, fermion gauge boson vertex, because that's the only coupling, right? And so basically you need these for all the fields that could be external length. Good. Then we said that the word identities will relate the counterterms that we saw in the case of QED. We took the gauge boson self-energy, wrote down the contribution of a whole bunch of terms. I very quickly argued that the awfully divergent part, which was proportional to the gamma function 1 minus d over 2, in dim reg is horribly offensive. The coefficient of it is cancelled, luckily, but that was guaranteed. But non-perturbative we argued for that. And then the coefficient of the other term, the log term, which was gamma 2 minus d over 2, was we found it to be gauge dependent, right? Do you guys recall this? We did this calculation for the QED as well. It turned out to be gauge dependent as well, if you recall, right? The expression would look simpler, but it was still the same, right? So it's gauge dependent. All right. Any questions?
But
yeah.
How did the people who cooked up the Erasmus symmetry come up with it? Is it just like there's a random thing that came up with that thing, or is there a deeper reason as to why?
No, there's a very so the deeper reason comes from the fact that gauge theories are like there's a full study. There's a high level study of constraint systems. So gauge theories are examples of constraint dynamics. And if you just want to formally talk about the quantization of constraint systems, this the whole BRC symmetry was a formal prescription in mathematical physics people had built for quantization of constraint systems, including gauge theory. Gauge theories are special cases. Now, of course, later on, people wrote down the BRC transformation for QCD, but there's a long history of this. There's a very nice book on like this whole story at high level. How do you go about quantizing these systems that are constrained? So there's first level constraint, second level constraint. It's a long story. I'm not an expert on that stuff, but yeah. There's quite a bit. Like people spend their whole life studying stuff.
So you mentioned gauge theories, and you mentioned them in general and not just the whatever the F squared term.
Yeah. So, well, actually, that is the canonical term, the conventional term we replicating various things. There's really that has local dynamics. The other things we can write down are logical, so they don't have local dynamics. We saw that actually from the lattice, if you recall, right? From the lattice, we saw that this term pops up. So it's not shocking. In the derivative expansion, we saw that this is the very first non-trivial term. Now, over there, I was sloppy about well, I didn't explain the possibility of a topological term. That's fancy, but yeah. Any other questions? That was my last slide, yeah.